Tonight, we're going to follow two spacecraft to the edge of everything we know, and then a little further than that. You've heard their names. You may even think you know the story. But here's what most people don't realize. The two machines we sent are still out there, still moving, still ours. And the silence everyone calls losing contact was written into the plan from the first day. By the end of tonight, you're going to understand why they will outlast every one of us, why that long quiet ahead was never a failure, and what it means that something we built will still be traveling long after the last person who remembers it is gone. If that sounds worth sitting with, you're welcome to follow along. We begin now. It started with a photograph that was supposed to be boring. The year was 1979. The place was a quiet room at the Jet Propulsion Laboratory in the hills above Pasadena, California, where the people who fly spacecraft sit in front of screens for hours and look at things most of us would never think to look at twice. One of those people was a navigation engineer named Linda Morabito. Her job that week was not glamorous. It was arithmetic made of starlight. A spacecraft called Voyager 1 had just swung past Jupiter. To know exactly where it was, Morabito needed to measure its position against the fixed stars behind it. So she pulled up an image of one of Jupiter's moons, a small, sulfur-colored world called Io, and she went looking for faint stars near its edge. Reference points, nothing more. The moon itself was not the subject. It was just the thing in the foreground, the way a street light is just the thing in front of the constellation you're actually trying to find. She brightened the image to bring the dim stars out, and there, rising off the edge of Io, was something that did not belong. It was a soft, curved plume, a pale umbrella of light standing up off the limb of the moon, hundreds of miles tall, leaning slightly, like smoke caught in a still room. It was not a star. It was not a flaw in the film. It was not the spacecraft. It was coming from the moon. She sat with it for a moment. This is the part worth slowing down on, because moments like this are rarer than they sound. Most discoveries arrive buried in months of analysis. This one arrived the way a sound arrives in a dark house, all at once and impossible to unhear. What she was looking at was a volcano, an active one, erupting right then on another world, 400 million miles from the room she was sitting in. Nothing like it had ever been seen. Until that night, the Earth was the lively one, and everything else was supposed to be cold, finished, geologically asleep. Io was a small moon, smaller than the one that lights our own sky. By every reasonable expectation, it should have been a dead gray rock, cratered and quiet, the way our moon is quiet. It was not quiet. It was the most volcanically violent place anyone had ever found, and a spacecraft built to simply pass by had caught it in the act, almost by accident, in an image taken for a completely different reason. That is the thing about these two machines, and it is the thread we are going to follow all night. They were sent to take measurements. What they actually did, again and again, was walk into rooms in the dark and turn on a light no one knew was there. They kept finding the universe being stranger and warmer and more alive than the careful people who built them had dared to assume. And Io was only the first room. Before we follow the rest of the path, before the rings, the tilted world, the last planet, and the long quiet after, it's worth seeing exactly how impossible that little moon really was. Think about the size of it. Io is a modest ball of rock and sulfur, not much bigger across than the moon you can see from your back step on a clear night. A world that small should have lost its inner heat long ago, the way a small stone cools faster than a boulder. Small things in space go cold. That is the rule. Io broke it. The plume Morabito saw was throwing material nearly 200 miles straight up off the surface, fast enough to escape the moon's gravity entirely. Not lava creeping down a slope. A fountain standing up into space, taller than any mountain on Earth, fed from somewhere deep inside a world that had no business still being warm. The reason it turned out is that Io is being needed. It runs between giant Jupiter and the pull of the other large moons, and it gets squeezed and released on every orbit until the friction of that flexing melts its insides. It is heated not by fire, but by being endlessly worked, like a piece of metal warmed by bending it back and forth in your hands. A small world kept alive by the company it keeps. Hold on to that idea. It comes back tonight in stranger forms, more than once. But to understand how a single image taken for navigation became one of the great surprises of the century, we have to go back a little. Back before Jupiter. Back before either spacecraft had left the ground. Back to a young man with a pencil who noticed that the planets were about to line up in a way they would not line up again for a very long time. In the summer of 1965, a young aerospace engineer named Gary Flandreau was given what sounded like a small assignment. He was working as a summer student at the Jet Propulsion Laboratory, and his task was to survey possible trajectories for missions to the outer planets. Jupiter, Saturn, Uranus, Neptune. The lab wanted to know what was theoretically reachable, and when. Flandreau began running the numbers. What he found changed the shape of the next 4 decades of space exploration. The outer planets, he calculated, were arranging themselves in a rare alignment. Not a straight line. The solar system does not arrange itself in straight lines, but a slow arc, a favorable curve, one planet leading to another in a sequence that would allow a single spacecraft to use each planet's gravity to sling itself to the next, gaining speed for free, like a ball passed hand to hand down a line. A spacecraft launched at the right moment could visit Jupiter, then Saturn, then Uranus, then Neptune, all in a single continuous journey, without needing fuel for each leg. The window for that journey opened in the late 1970s. It would close and not open again for approximately 176 years. Flandreau was 25 years old when he worked that out. The idea became known as the Grand Tour, and it set off a long, complicated period of planning and funding arguments and redesigns, the kind of institutional turbulence that tends to swallow ambitious ideas whole. The original plan involved 4 spacecraft with an enormous budget. What eventually emerged, after years of cuts and negotiations, was leaner and stranger and ultimately more remarkable. 2 spacecraft, built quickly, built affordably, built to last a few years in space and then go quiet. They were called Voyager 1 and Voyager 2. Voyager 2 lifted off from Cape Canaveral on August the 20th, 1977, a warm Florida morning. Voyager 1 followed 16 days later, on September the 5th. Despite their names, Voyager 1 launched second. It was aimed on a faster trajectory and would overtake its companion within a few months. They were traveling to the outer solar system, but in a deeper sense, they were traveling towards something no one could fully define. A science mission, certainly, a navigation test, but also, and this feeling lived in the people building them even if it wasn't written in any specification, something like a letter dropped into a river and addressed to the universe. Each spacecraft carried 12 scientific instruments, cameras, magnetometers, instruments to measure charged particles, cosmic rays, plasma, radio waves. They weighed about 900 kilograms each, lighter than a small car. Their power came from the decay of radioactive plutonium, a quiet nuclear heart that asked for nothing and gave off a slow, steady warmth. They had no ability to steer themselves toward a target, stop, look around, and decide where to go next. Their whole path was calculated in advance, from gravity wells and angles and the positions of worlds that had been moving on their predicted courses for billions of years without asking permission. What Flandreau had found was not a door that anyone built. It was a door that the solar system had been slowly, indifferently opening for 176 years, and it would hold open for long enough to let two carefully aimed objects pass through. We threw them through it. The moment of launch is worth sitting with for just a second. At the top of a Titan Centaur rocket, in the shuddering minutes before ignition, the spacecraft waited. All the mathematics, Flandreau's alignment, decades of trajectory calculations, the painstaking instrument calibrations, was on the inside, inert, waiting for velocity. The universe that the spacecraft would spend decades crossing was out there, indifferent and enormous. Between the two, a few seconds of controlled fire and a vector. And still they moved outward, the way they always had. Not yet with purpose, just with speed and heading and the quiet company of physics. Ahead of them, the asteroid belt, a region everyone imagined as a wall of tumbling rock. Ahead of that, a storm older than the oldest living thing on Earth. Ahead of all of it, a series of answers that no one had specifically asked for, given freely to a species that had been watching these planets as points of light for all of recorded history and had never yet come close. Everyone who watched science fiction in the 1970s had the same mental image. The asteroid belt was a wall, a churning, grinding field of rock and debris, the kind of obstacle a spacecraft had to carefully thread, dodging at the last second, instruments alert. That was what movies and illustrations had taught us. It was almost entirely wrong. The question of whether a real spacecraft can survive the crossing had been genuinely open, not as a dramatic uncertainty, but as a serious engineering concern, the kind that gets written into mission risk assessments and discussed in rooms with whiteboards and coffee cups. Nobody had sent anything through. The cameras on Earth could see the larger asteroids, but the small ones, the sand grain and pebble-sized material that could chip a solar panel or pit a sensor window, those could not be counted from here. The worry was not collision with a boulder. The worry was sandblasting. In the spring of 1972, a mission called Pioneer 10 was aimed directly at the belt. The man responsible for getting it through in one piece was a project manager at NASA's Ames Research Center named Charles Hall, a careful, methodical engineer who had spent years preparing for a transit no one could fully simulate. The spacecraft crossed the inner edge of the belt in July of that year. Nothing happened. Pioneer 10 drifted through, recorded a modest increase in dust impacts, found that the feared sandblasting was real only in the loosest theoretical sense, and emerged on the other side with all its instruments intact. Hall and his team had built something that survived something that turned out to be barely a challenge. The anticlimax was the finding. By the time Voyager 1 and Voyager 2 made the same crossing, a few years later, the engineers had Pioneer's data to work from. The belt was still there. It still held roughly 1 million objects large enough to name. But the truth underneath all those numbers was the kind of truth that quietly reshapes how you think about scale. The asteroid belt is enormous. Stretch it flat, fill it with everything in it, and you are still left with a region of space so vast that the average distance between objects large enough to do any real damage runs into the hundreds of thousands of miles. There's more nothing in the asteroid belt than there is anything. The reason a spacecraft can cross it without a single collision is not luck. It is that space is, by almost any measure we have, almost entirely empty, and the belt is space first and rock second. Voyager's crossings produced a data point that the scientists noted and filed, a modest uptick in particle impacts. Then the numbers settled back down, and ahead of both spacecraft was a brightening point of light that had been growing for months. Jupiter. You can track the approach of something enormous in space long before it becomes what you expected. The first signals Voyager returned from Jupiter's vicinity were not images. They were changes in the radiation environment, a deepening hum of charged particles, the electromagnetic signature of a magnetic field far larger than anything in the inner solar system. Jupiter broadcasts its presence across hundreds of millions of miles. The spacecraft were inside that broadcast long before they were close enough to take a picture worth keeping. What is worth knowing here, before the images began to arrive, is something about the mindset of the people watching the data scroll in. These are scientists who had spent years building instruments to measure things they expected to find. They had theories. They had predictions. They had decades of observations from Earth-based telescopes that had told them, more or less, what Jupiter should look like up close. A gas giant, a storm, some moons, the known and the expected. That is always the most dangerous moment in science. The moment you are most confident you know what you're walking into. Not because nature is malicious or secretive, but because the universe is not organized around human expectations. And it doesn't warn you before it hands you something your framework wasn't built to hold. The pictures began to arrive in the winter of 1978. While the spacecraft were still tens of millions of miles out. Each one was better than the last. The storm resolved. The cloud bands sharpened. The moons became disks, and then worlds. And then, for one navigation engineer in a quiet room, staring at a detail she had almost discarded, something that changed everything. We have been there already. Now it is time to take the full measure of what surrounded it. In the summer of 1965, a young aerospace engineer named Gary Flandreau was given what sounded like a small assignment. He was working as a summer student at the Jet Propulsion Laboratory, and his task was to survey possible trajectories for missions to the outer planets, Jupiter, Saturn, Uranus, Neptune. The lab wanted to know what was theoretically reachable, and when. Flandreau began running the numbers. What he found changed the shape of the next 4 decades of space exploration. The outer planets, he calculated, were arranging themselves in a rare alignment. Not a straight line. The solar system does not arrange itself in straight lines, but a slow arc, a favorable curve. One planet leading to another in a sequence that would allow a single spacecraft to use each planet's gravity to sling itself to the next, gaining speed for free, like a ball passed hand-to-hand down a line. A spacecraft launched at the right moment could visit Jupiter, then Saturn, then Uranus, then Neptune, all in a single continuous journey, without needing fuel for each leg. The window for that journey opened in the late 1970s. It would close and not open again for approximately 176 years. Flandreau was 25 years old when he worked that out. The idea became known as the Grand Tour, and it set off a long, complicated period of planning and funding arguments and redesigns, the kind of institutional turbulence that tends to swallow ambitious ideas whole. The original plan involved 4 spacecraft with an enormous budget. What eventually emerged, after years of cuts and negotiations, was leaner and stranger and ultimately more remarkable. 2 spacecraft built quickly, built affordably, built to last a few years in space and then go quiet. They were called Voyager 1 and Voyager 2. Voyager 2 lifted off from Cape Canaveral on August the 20th, 1977, a warm Florida morning. Voyager 1 followed 16 days later, on September the 5th. Despite their names, Voyager 1 launched second. It was aimed on a faster trajectory and would overtake its companion within a few months. They were traveling to the outer solar system, but in a deeper sense, they were traveling towards something no one could fully define. A science mission, certainly, a navigation test, but also, and this feeling lived in the people building them even if it wasn't written in any specification, something like a letter dropped into a river and addressed to the universe. Each spacecraft carried 12 scientific instruments, cameras, magnetometers, instruments to measure charged particles, cosmic rays, plasma, radio waves. They weighed about 900 kilograms each, lighter than a small car. Their power came from the decay of radioactive plutonium, a quiet nuclear heart that asked for nothing and gave off a slow, steady warmth. They had no ability to steer themselves toward a target, stop, look around, and decide where to go next. Their whole path was calculated in advance, from gravity wells and angles and the positions of worlds that had been moving on their predicted courses for billions of years without asking permission. What Flandreau had found was not a door that anyone built. It was a door that the solar system had been slowly, indifferently opening for 176 years, and it would hold open for long enough to let 2 carefully aimed objects pass through. We threw them through it. The moment of launch is worth sitting with for just a second. At the top of a Titan Centaur rocket, in the shuddering minutes before ignition, the spacecraft waited. All the mathematics, Flandreau's alignment, decades of trajectory calculations, the painstaking instrument calibrations, was on the inside, inert, waiting for velocity. The universe that the spacecraft would spend decades crossing was out there, indifferent and enormous. Between the two, a few seconds of controlled fire and a vector. And still they moved outward, the way they always had. Not yet with purpose, just with speed and heading and the quiet company of physics. Ahead of them, the asteroid belt, a region everyone imagined as a wall of tumbling rock. Ahead of that, a storm older than the oldest living thing on Earth. Ahead of all of it, a series of answers that no one had specifically asked for, given freely to a species that had been watching these planets as points of light for all of recorded history and had never yet come close. the crossing began, and the first thing between home and Jupiter was the kind of emptiness that is almost impossible to describe without getting it wrong. Imagine descending through a sky with no ground beneath it. Cream and amber clouds spread out in every direction, slow and wide and soft, layered one beneath another like the pages of something ancient. The wind here is not a single thing. It moves in bands, vast rivers of air flowing east, while the river beside them flows west, and where they meet the edges curl and fold into spirals that stretch for thousands of miles without breaking. The light comes from above, diffused through so many layers of cloud that it arrives pale and even, casting no shadows. Below, the color shifts. Amber deepens to rust. The clouds thin into something darker, and deep inside that darkness, a pulse of light opens and closes in silence. Lightning wide as a continent, moving no faster than a slow breath. And still the clouds drift on, and the colors settle, and the whole vast turning world hums at a frequency you feel rather than hear, low and steady, patient and unchanged. The great red spot had been turning before anyone alive had been born, before anyone's grandparents had been born, before the United States existed, before the steam engine, before the Industrial Revolution rearranged the surface of this planet. The Italian astronomer Giovanni Cassini observed what appears to be the same storm in 1665, a permanent oval mark on the face of Jupiter that swirled in his telescope's lens and was still swirling, still there, still red, when Bradford Smith and the Voyager imaging team pulled up the first high-resolution pictures in the spring of 1979. At least 350 years, possibly longer. We simply do not know when it began, because we were not watching. The images that arrived were not what anyone had expected to feel. Scientifically, Jupiter had been understood in rough outline for years. The bands, the zones, the mass, all of it had been modeled. What the models had not prepared anyone for was the texture. Jupiter in the Voyager images looked alive in a way that photographs of a gas giant simply aren't supposed to look alive. The bands were not smooth. They churned. They knotted against each other at the seams. The great red spot was surrounded by smaller storm systems that wrapped around it like debris caught in a drain. And within the oval itself, the clouds moved in long, slow spirals that stretched and folded and came back around, patient and enormous and indifferent to the tiny machine watching from above. Here's how large it is. At the time Voyager flew past, the storm was wide enough to place 2 Earths side by side inside it and still have room. Not metaphorically, not approximately. 2 full-sized planets, your planet, the one outside your window tonight, and another just like it, dropped inside a single storm, on a single world, 400 million miles away, and the storm swallows them both. Jupiter's gravity had collected more material than everything else in the solar system combined, not counting the sun. More than 1,000 Earths could fit inside its volume. It is not a large planet in the way that the word large is normally used. It is a different category of object, a world so massive that its gravity has been quietly shaping the rest of the solar system since the beginning, flinging some objects inward, holding others at bay, keeping the asteroid belt from ever collapsing into a planet of its own. And that gravity, that relentless kneading pull, was exactly the thing keeping Io alive. The mechanism Morabito had found in her navigation image, the volcanic plume, the active interior, was Jupiter's work. The moon had no choice but to be warm. The same hand that threw the storm into its centuries of spinning was squeezing the small sulfurous world in its inner orbit like a stone in a fist. The encounter team worked in shifts. Thousands of images came in. Each one was processed, cataloged, scrutinized. There were moments, Smith later described, when the whole room would go quiet. Not because something had gone wrong, but because something had arrived that no one had words for yet. Jupiter was not the background for the discovery of Eo's volcanoes. It was its own discovery, the kind that happens when you are close enough for the first time to stop working from theory and start working from what is actually in front of you. Then the spacecraft came around the far side of Jupiter and aimed outward, and the giant fell behind them, and the pull of its gravity became something else. Speed. A gift of velocity, borrowed from a world that will not notice the lending for another 4 billion years. Ahead of Voyager, one lay Saturn, and a moon with an orange haze, and a choice that would define the rest of the mission. Ahead of Voyager, two lay the same Saturn, and after that, two worlds that no machine had ever seen up close. But before we follow them there, before the rings, before the tilted planet, before the last flyby at the edge of the known solar system, it is worth resting for a moment inside the kind of world they were leaving behind. The first images of Europa came back looking wrong in the most interesting possible way. Not wrong like a malfunction. Wrong like a world that had been playing by different rules than every other piece of rock and ice the mission had encountered so far. The moon's surface was smooth, extraordinarily, almost artificially smooth, where the other Jovian moons were pockmarked with craters, scarred by billions of years of impacts, rough and honest in the way that old things tend to be. Europa was clean, polished, as if something had recently resurfaced it, or was continuously resurfacing it, smoothing out the record of everything that had hit it. And across that smooth face ran lines, thousands of miles of them, brown-orange cracks cutting across the pale ice in long arcs and curves, intersecting and overlapping, the whole surface crisscrossed like something that had been stretched until it fractured. Bradford Smith's imaging team stared at those lines for a long time. What they were seeing, they slowly came to understand, was not a dead surface at all. It was the ceiling of something. The cracks were places where the ice had pulled apart and refrozen, evidence of movement below, of a shell that was flexing, very slowly, under the same gravitational stress that kept Io volcanic. But Europa, being farther from Jupiter, was not being heated enough to melt to rock. It was being heated just enough, many scientists believed, to maintain liquid water beneath the ice. An ocean, a real one, sealed under a shell of ice, in the dark, never touched by sunlight, never connected to the sky above it. The idea settled over the scientific community slowly, the way important ideas often do, not as a single dramatic announcement, but as a growing consensus, one paper and one data set at a time. What emerged was this: Europa may hold more liquid water than every ocean on Earth combined. In a shell of ice, the thickness of a city, a hidden sea may descend to depths roughly 10 times greater than the deepest point in any ocean on this planet. That is worth holding still for a moment. On a moon most people have never heard of, smaller than our own moon, in perpetual darkness, under ice, there may be more water than this planet has ever seen on its surface. and where there is water, and where there is heat, and where the chemistry of a seafloor meets the patience of deep time. Well, the people who study such things do not say life, not from Voyager data, not yet. They say conditions are not obviously hostile, which, in the careful language of science, is one of the loudest things you can say. The spacecraft could not look beneath the ice. It had cameras for surfaces and instruments for fields and particles. Not sonar, not a submarine. It flew past, took its pictures, returned its data, and moved on. The ocean, if it exists, is still down there, still sealed, waiting for something with better tools and more time. And still they moved outward, the way they always had, past Europa, past the whole Jovian system, growing smaller now in the instrument's rear view, its magnetic field fading, the particle counts dropping back toward the low background hum of interplanetary space. Saturn was ahead, still more than a year away in travel time, still hundreds of millions of miles in the dark. The spacecraft were aimed and patient, burning no fuel, following the arc of the Grand Tour that Flandreau had mapped from a desk in Pasadena, trusting gravity to do the work. If you have found something in tonight's journey worth holding on to, a quiet sense of how strange and alive these distant places are, then a like and a subscription means the next journey finds you when it's ready. We'll be here. For now, we move on, because ahead of Voyager lay something that, even from a distance of hundreds of millions of miles, even seen only as a smear of light through a ground-based telescope for 3.5 centuries, had always looked different from everything else in the sky. A planet ringed. A planet that looked, when you first saw it properly, like something someone had imagined, rather than something that simply occurred. Saturn was waiting, and the closer the spacecraft drew, the stranger the mathematics of what they were approaching became. Saturn had been known to have rings since Galileo first pointed a telescope at it in 1610, and wrote that the planet appeared to be accompanied by 2 smaller bodies, one on each side, as if it had ears. He did not understand what he was seeing. When he looked again 2 years later, and the ears had vanished, the rings edge on, invisible from Earth at that angle, he suspected the planet had somehow consumed its companions, and wrote in his notebook that Saturn had devoured his own children. He died without ever knowing he had seen a ring at all. By the time Voyager 1 made its closest approach to Saturn in November of 1980, the rings had been studied for 3.5 centuries. They were known to be wide. They were known to be made of ice and rock. The broad structure, the A ring, the B ring, the dark gap of the Cassini division between them, had been cataloged and named and modeled. The community had a picture. It was detailed and confident, and, it turned out, incomplete in ways that delighted everyone who found out. A young scientist named Carolyn Porco was part of the imaging team working the Saturn data as it arrived. She had spent years focused on the rings, thinking about their dynamics, building models of how particles under Saturn's gravity should behave. The images that came back did not break her models. They made them seem like sketches compared to the thing they had been trying to describe. The rings were not smooth bands. They were made of thousands of individual ringlets, thin concentric structures packed inside each other, each one a river of ice particles in its own orbit. The whole system more like the grooves on a vinyl record than anything the pre-Voyager maps had suggested. And within the B ring, the thickest and brightest of them, something stranger still, dark spokes, radial marks fanning outward from the planet, rotating not with the particles of the ring, but with Saturn's magnetic field. They moved like the hands of a clock, in defiance of what orbital mechanics said they should do, and no one could immediately explain them. But the number that stays with you, the one that changes the scale of the whole image in your head, is not the width or the number of ringlets or the mystery of the spokes. It is the thickness. The main rings of Saturn span more than 170,000 miles, from their inner edge to their outer edge. That distance is roughly 3/4 of the way from the Earth to the Moon. The rings are wider than a planet. If you stood at one edge and looked across, the other side would take a powerful telescope to find. And yet in places, the rings are roughly a few hundred feet thick. Some sections perhaps 1,000 feet. No more. Take a sheet of paper, hold it at arm's length. That sheet of paper, scaled up to the width of the ring system, would be thicker than the rings are, by a considerable margin. An object spanning 3/4 of the Earth-Moon distance is also, in cross-section, shorter than a tall building. The material is there, billions of particles, ice chunks ranging from dust grains to objects the size of a house, but spread across such an unimaginable width that the average density in any cross-section is almost nothing. The universe does this repeatedly, offers you something that sounds impossibly grand, and then shows you, from a different angle, how thin the grandeur actually is. Porco and the rest of the team worked through the data for months. Not just the rings, the moons too. Saturn had many more of them than anyone expected to find so close together, shepherding the ring edges, carving the gaps, pulling the particles into braided structures with their gravity. The mission had arrived at a world that was running several systems simultaneously. Rings, moons, magnetic field, the massive planet itself, and each system was more elaborate than the one before it. Voyager 2 made its own Saturn encounter in August of 1981, 9 months after Voyager 1. By then the team knew more than they had the first time. They were better questions. But for Voyager 1, the Saturn encounter ended with a choice that was not really a choice at all. North of Saturn, in an orbit that looked wrong from a distance, and stranger the closer you got, was a moon shrouded entirely in thick orange haze. Scientists had suspected it might have an atmosphere. They wanted to know. And to find out, the spacecraft would have to be redirected, swung low and close in a trajectory that would answer the question about the moon, and in doing so, throw Voyager 1 up and out of the plane of the solar system forever, away from every remaining planet, onto a path no world would interrupt again. It was an easy decision. The moon was worth it. There is a moment in mission planning when the spreadsheet stops being abstract and becomes a genuine negotiation with the universe. You have a spacecraft. You have a limited supply of velocity, time, and luck. You have a list of things worth seeing, and you do not get to see all of them. Someone has to decide which things you give up. For Voyager 1, that decision had been made years before launch, quietly and deliberately, by a team of scientists and trajectory planners who understood what they were trading. The project scientist, Ed Stone, and the mission planning team had looked at the outer solar system and concluded that one object was worth the price of every other object Voyager 1 had not yet visited. That object was Titan, Saturn's largest moon, the one wrapped in a hood of thick orange haze, so opaque that no telescope had ever seen through it to the surface below. Titan had been mysterious for decades. Unlike every other moon in the solar system, it had an atmosphere. A real one, thick and complex, rich in nitrogen and organic chemicals. Carl Sagan had theorized that the chemistry happening in those clouds might resemble the chemistry of early Earth before life rearranged the inventory. Whether he was right or not, the scientists wanted to know what was underneath, and the only way to find out was to go very close. The trajectory Voyager 1 flew past Titan was precise and costly. It dipped low, threading through Saturn's system on an arc calculated to maximize the science return from the moon. The spacecraft's instruments pressed against the haze. The cameras tried to see. What they found was that the atmosphere at Titan's surface exerts a pressure roughly 1.5 times greater than the air resting on your shoulders right now. Denser than Earth's sky, heavy with cold chemistry. A world underneath it that would remain unseen until a different mission, decades later, finally sent a probe down through that orange ceiling to find rivers and lakes of liquid methane waiting patiently below. Voyager 1's cameras saw only haze. Layer after layer of orange and brown, no surface, no feature. A world hiding behind its own weather. The scientific instruments measured the atmosphere's composition and temperature and thickness. It was not nothing, but it was not the surface. And then the flyby was over, and gravity did what gravity does when you get close and then leave. It pushed back, bent the path, and sent Voyager 1 not onward toward the remaining planets, but upward, out of the flat plane of the solar system, climbing away from the ecliptic at an angle it would hold for the rest of its existence. Uranus was behind it now, in the sense that the trajectory made it unreachable. Neptune too. Every remaining world in the outer solar system was below and behind, accessible to Voyager 2, which had been given a different trajectory, precisely because Voyager 1 was spending its planetary tour on this. The trade was worth it, Stone and the others would say later. Titan's atmosphere was a discovery. The grand tour was not abandoned. It was divided. One spacecraft went up and outward, into the permanent dark between the planets. The other kept going. We will follow Voyager 2 in a moment. But first, somewhere between Saturn and the edge of the planetary solar system, before the missions diverged in every meaningful sense. It is worth noting that the space through which both spacecraft were still traveling, for all its apparent emptiness, was far from featureless. There's a texture to the dark between the planets, a slow, ancient stillness that the instruments recorded and that no photograph has ever quite managed to show. Out beyond the known orbits, small worlds turn slowly in the dark. A piece of iron the size of a building rotates once every few hours, unhurried, as if considering some private question. Sunlight falls across its surface at a low angle, catching the olivine and iron in a color between rust and gold, warming one face, while the other rests in a cold so absolute it has no counterpart on Earth. Another rock drifts past at a distance of many thousands of miles, its shadow trailing behind it like a thought that has not finished forming. There is no sound here, and no wind, and nothing moves quickly. Each stone has been turning in roughly this way for 4 billion years. They are not waiting for anything. They are simply here, in the way that very old things are simply here. Without urgency, without memory, present in the dark the way the dark itself is present, completely and without effort. Voyager 2 was alone now, in the way that machines in deep space are alone, moving through a silence that would have been incomprehensible to anyone standing in the building where it was built. Voyager 1 had already curved upward out of the ecliptic, gone. Ahead of Voyager 2, still 2 years of traveling away, was a planet that had been bothering astronomers for 2 centuries. Something had gone wrong with Uranus, and no one could quite agree on when. Every other planet in the solar system spins on an axis that stands roughly upright relative to its orbit, tilted a few degrees, maybe more, but always with a recognizable top and bottom. Earth's axis leans about 23 degrees, which is how we get seasons. Saturn tilts about 27. Even Jupiter, which spins nearly perfectly upright, is close to the familiar geometry. Uranus tilts 98 degrees. It is not spinning around a vertical axis. It is rolling around the sun on its side, like a ball being pushed rather than a top being spun. Its poles point almost directly at the sun and then directly away from it. One pole endures 42 years of continuous daylight. The other endures 42 years of continuous dark. Something hit it, long ago. Something enormous probably, during the era when the solar system was still sorting out who got to be where. Whatever it was left, no calling card, only the tilt. On January the 24th, 1986, Voyager 2 made its closest approach. The encounter team at JPL had been building toward this for years. Brad Smith's imaging group, the magnetometer team, the plasma scientists, all of them finally within range of the last unvisited giant. They gathered around their screens, as they had at Jupiter and Saturn, ready for the camera to return something extraordinary. Uranus gave them almost nothing. The images showed a blue-green disk, smooth and blank, as featureless as a billiard ball. No storms, no bands of cloud, no great red spot equivalent. Just an even pale color, methane in the upper atmosphere absorbing the red wavelengths, leaving only blue and green, blending together into something that looked less like a planet than like a color swatch. The cameras had traveled nearly 2 billion miles and found a world that apparently had nothing to say. It was deeply strange, and underneath the strangeness was a number that made it stranger still. Uranus is the coldest planet in the solar system. Not Pluto, which is farther. Uranus. The temperature at its cloud tops has been measured at around 371 degrees below 0 Fahrenheit. And here is what makes that wrong in the most interesting way. Every other giant planet radiates more heat than it receives from the sun. They are still cooling from their formation, still giving off the warmth of their own making. Uranus radiates almost nothing. It receives heat from the sun, and it gives back almost exactly that much and no more, as if the collision that tipped it over also did something to its interior, knocked something loose, sealed something off, left it unable to bleed its own warmth into space. It sits in the dark, the coldest world in the solar system, rolling silently on its side, and it has never adequately explained itself. The encounter team had 4 days to work with the data before the world's attention moved elsewhere. On January the 28th, 4 days after the Voyager 2 flyby, the Space Shuttle Challenger broke apart 73 seconds after launch. The news came in while JPL was still processing Uranus in the way that real events work, indifferent to each other, sharing a calendar without sharing any meaning. One of the most distant planetary encounters in history, and one of the worst days in American space exploration occupied the same week. The scientists kept working. There was data to process and a spacecraft to track, and it was still going. 3 years and more than 1 billion miles of travel still separated Voyager 2 from the last planet on its itinerary. Neptune was waiting, a world at the edge of the classical solar system, colder and stranger than Uranus, with a moon that should not have been in the orbit it was in. And somewhere in the nitrogen plumes rising off that moon's surface, Voyager 2 was about to find the last great surprise of its planetary tour. And still, they moved outward the way they always had. Neptune had waited longer than any planet for a visitor from Earth. It had been discovered with mathematics before it was discovered with a telescope. In 1846, astronomers noticed that Uranus was being pulled by something unseen, mapped the disturbance back to its source, and found a new world exactly where the equations said it should be. That was Neptune's introduction, a ghost that left tracks in the gravity of another planet. It announced itself through its influence on the things around it, and then sat at the edge of the solar system for 143 years, visible only as a pale blue point, until August of 1989, when Voyager 2 completed the longest single planetary journey any human-built object had ever made. The encounter team at JPL had grown comfortable with surprises by this point. 3 planetary systems had each handed them something they had not expected. Neptune, they assumed, would do the same. They were right. The first surprise was in the planet itself. A massive storm, dark and oval, so structurally similar to Jupiter's Great Red Spot that the team took to calling it the Great Dark Spot almost immediately. A storm stretching 12,000 miles across, rotating counterclockwise, sitting in the upper atmosphere of a world nearly 3 billion miles from the Sun. But the stranger object was the Moon. Triton had been known since 1846, discovered only 17 days after Neptune itself. What nobody had been able to determine from Earth, despite nearly a century and a half of observation, was which way it was going. As Voyager 2 approached, it became clear. Triton orbits Neptune in the opposite direction from Neptune's rotation. Every other large moon in the solar system orbits the same way its planet spins. Triton runs backward. There's only one way to end up going the wrong way around a planet. You are not formed there. Triton formed somewhere else in the early solar system, traveled alone for millions or billions of years, and then wandered too close to Neptune. The planet's gravity caught it, pulled it in, and bent its path into the orbit it still traces today. A captured wanderer, still working off the energy of its capture, slowly spiraling inward, not going anywhere on any timescale that matters to us, but committed by physics to an ending. In roughly 3.5 billion years, Triton will come close enough to Neptune that the tidal forces will tear it apart, and the pieces will spread into a ring. Neptune will wear its moon like Saturn wears its rings, eventually. For now, it is still orbiting, still whole, still running backward. A scientist named Lawrence Soderblom was part of the team analyzing Triton's surface as the images resolved. What came in was unlike anything the mission had seen. The terrain was textured in a way that had never appeared on another world. a bumpy, crenellated surface the team called cantaloupe terrain, not because they knew what caused it, but because it looked like the rind of a melon seen from above. And near the South Pole, across a pale pink sheet of nitrogen ice, Soderblom noticed something subtle: dark streaks, long dark smears trailing in the same direction again and again, as if something had been blown across the surface. The team looked closer. The streaks were plumes, nitrogen geysers rising several miles above the surface before being caught and dragged downwind. On one of the coldest surfaces measured in the solar system, at a temperature of 391 degrees below 0 Fahrenheit, heat from the sun was somehow penetrating a thin layer of transparent nitrogen ice, warming the dark material beneath it, and building pressure until it vented upward. A world colder than anything we can fully experience, leaking heat through its own ice, making geysers out of the sun's faint touch. You could feel, in the data coming in, the spacecraft's instruments straining at the edges of their design. Neptune was so far from the sun that the power available for photography was a fraction of what it had been at Jupiter. The images were darker. The signals took longer, but they kept coming, each one pulled across more than 2.5 hours of space at the speed of light, arriving at the Deep Space Network antennas in the California desert and the Atacama and outside Canberra, assembled into pictures of a world no human eye would otherwise have seen in this century. Neptune's clouds moved at nearly 1,200 miles per hour, the fastest sustained winds on any planet we know, a world at the far edge, cold and blue, violent with its own weather, ancient and strange. The flyby lasted less than a day. Then it was behind them. There would be no more planets. Carl Sagan had been trying to get the picture for more than a decade. The idea was simple enough to explain in a single sentence, and Sagan did explain it, many times, to many people who were not convinced. Turn Voyager 1's camera around. Point it back at the sun. Take a photograph of the solar system from the outside. Not a close-up of a single planet, not a navigation image, not a scientific measurement of anything in particular, but a portrait. The whole family from a distance, no human eye had ever managed. The resistance was practical. The camera systems on Voyager 1 required pointing the spacecraft, which consumed fuel and time. The scientific teams had other priorities. The imaging system was already scheduled for shutdown. There were no more planets to photograph, and the power was needed elsewhere. And the picture, critics pointed out with some accuracy, would not tell us anything we did not already know. It was not science. It was something harder to budget for. Sagan kept asking. In 1990, with Voyager 1 traveling beyond the orbit of Neptune, the request was finally approved. On the 14th of February, Valentine's Day, which Sagan did not consider accidental, the spacecraft turned. The camera opened. 60 individual frames swept across the inner solar system, capturing the sun and 6 planets in a long mosaic from a distance of 3,700,000,000 miles. Earth appeared in one of those frames. Not clearly, not obviously. It took looking. The sunlight scattered inside the camera optics, creating streaks and bright bands, and somewhere inside one of those bands, a pale blue point, barely there, smaller than the period at the end of the sentence, was every human being who had ever lived, every city ever built, every war ever fought, every piece of music, every painting, every cruelty, every tenderness, the whole record of the species, every horizon anyone had ever stood at and looked out from. It occupied roughly 1/10 of a single pixel. Sagan wrote about the image, and what he wrote has been read more than almost anything else he wrote, which is saying something because he wrote a great deal. The core of what he said was not complicated. Look at what you are. Look at how small it is. And consider, for a moment, what that means about the things we treat as if they are the largest matters in the universe. He was not being dismissive. He was asking for perspective. He spent the rest of his life asking for it, in various forms, and the image was the purest form of the question. After the portrait was taken, the camera was powered down. There was no ceremony. A command was sent, the camera received it, and that was the end of Voyager 1 as a visual instrument. It had been looking outward for 12.5 years. It had seen Jupiter close enough to map its storm. It had watched Io's plume rise. It had recorded Saturn's rings in enough detail to keep scientists busy for decades. And on its last day with open eyes, it turned around and took a picture of where it had come from. Then it went blind and kept going. The distance it had covered by that day, 3.7 billion miles, sounds like a large number. In the context of what came next, it barely registers. The spacecraft was still inside the sun's sphere of influence, still surrounded by the sun's magnetic field and its stream of charged particles, still technically within our own star's domain. The real boundary, the place where the sun's reach finally gives out, was still ahead by billions of miles and several decades. And between here and there, nothing, essentially. No planets, no moons, no asteroids, no destinations. Just a slow and patient crossing. And still they moved outward, the way they always had. There's a place beyond the last galaxy in any given direction where the light simply stops. Not dramatically, not all at once. It thins the way the edge of a fire thins into warmth, and then into the memory of warmth, until there is nothing left to thin. In that place, the dark is not the absence of something that was here. It is the presence of something that has always been here. A stillness so complete, it has its own texture, faint and cool and without weight. There is no motion that does not belong to its own small system. No sound at all, no wind, nothing falling toward anything. The cold here is not hostile. It is simply what cold becomes when nothing has ever disturbed it. A fact as old as the universe itself, patient in the way that only things without want can be patient, drifting in an emptiness so wide that the word emptiness feels too small, too crowded, too much like a room with walls. Before either spacecraft left Earth, someone had to decide what to put on them. The decision to include a message at all was not automatic. The Pioneer 10 and 11 spacecraft, which had been launched earlier in the decade, had carried a small gold anodized plaque, a simple diagram showing a man and a woman, the spacecraft's origin in the solar system, and a few reference measurements for any intelligence that might find it. It was a gesture, modest and elegant. For Voyager, the scientists wanted to try something more ambitious, something that sounded less like a postcard and more like a portrait. Carl Sagan assembled a small committee. The creative director of the project was a writer and producer named Anne Druyan, who had been brought in to help curate the sounds and music of Earth. She and the team had a narrow window, weeks, not months, to make decisions that would, if things went improbably well, last longer than any other human creation in history. What they assembled was a gold-plated copper record, a physical disc 12 inches across, housed in an aluminum jacket, with a stylus attached so that anyone who found it would know, from the diagrams on the cover, how to play it. The cover also carried a map, a precise diagram showing the position of the sun relative to 14 pulsars, natural cosmic beacons whose frequencies are so distinctive that the map amounts to an address. If you find this, the map says, "Here's where we are from." The record holds 115 images encoded in audio. Sounds of earth, rain, wind, surf, fire, birds, the low resonance of a whale calling through deep water, music from across the world and across centuries, Bach and Beethoven, blues and folk songs, instruments from cultures that have no names for each other's instruments, greetings in 55 languages, the voice of a child, the sound of a heartbeat, and something stranger than any of those. Anne Druyan recorded her own brain waves. She sat quietly and allowed an electroencephalograph to record the electrical activity of her mind for just under an hour. That recording was compressed and encoded and placed on the record. It is there now, on both spacecraft, traveling through interstellar space, the pattern of one human brain in a moment of quiet thought. Druyan has described in interviews over the years what she was thinking about during that recording. She was thinking about the history of the planet, about love, about what it means to be alive and aware in a universe that seems mostly indifferent to the fact. She was also, though she did not say this publicly for many years, in the early hours of a realization that she was falling in love with Carl Sagan. They would marry the following year, but in that moment, it was only a feeling, unnamed, being written in electricity across the inside of her skull, being translated into a signal that was pressed into gold-plated copper and bolted to the side of a spacecraft aimed at forever. Whether anyone will ever find it is not really the point, and the people who made it knew that. The likelihood of any intelligent civilization intercepting either Voyager in the next several 100 million years is, by any reasonable calculation, extraordinarily small. The galaxy is vast. The spacecraft are tiny. The paths they travel lead nowhere in particular, past no stars close enough to matter, aimed at no destination. They will drift for a very long time without meeting anything at all. What the record does, regardless of whether it is ever found, is change the nature of the mission. A spacecraft carrying only instruments is a measuring device. A spacecraft carrying the sound of rain and the recording of a human brain thinking about love is something else. A declaration that the species that built it believed the universe might be listening and decided, just in case, to say something worth hearing. The design lifetime of the record is approximately 1 billion years. In that time, the sun will have expanded and brightened enough to make Earth's surface uninhabitable. The species that made the record may not exist in any recognizable form. The languages spoken in the greetings will certainly be unrecognizable. Every language spoken on Earth today will have changed beyond recognition in a tiny fraction of that time. The record will outlast us, outlast our languages, possibly outlast every trace of our civilization on the surface of this planet. And it will still be going, still sealed, still carrying the sound of a heartbeat and the pattern of a mind that was, for a moment, thinking about what it means to be here. In 1958, a young physicist at the University of Chicago named Eugene Parker submitted a paper to a scientific journal. The paper described something that did not yet have a name: a continuous flow of charged particles streaming outward from the sun in every direction, a kind of permanent wind blowing into space at enormous speed. Parker called it the solar wind. The reviewers rejected it. The idea was considered too outlandish, too inconsistent with the prevailing understanding of the space between planets, which most physicists had assumed was essentially empty and essentially still. One reviewer described the paper as containing errors so fundamental that it could not be accepted. The editor overruled the reviewers and published it anyway. 4 years later, instruments aboard the Mariner 2 spacecraft confirmed exactly what Parker had described: a real wind, a constant stream, washing outward from the sun in all directions at roughly 1,000,000 miles per hour. Parker lived long enough to have a spacecraft named after him. What that wind does on the scale of the solar system is extraordinary. It flows continuously outward, not as a single event, not as a storm that comes and passes, but as a permanent condition, the sun losing a small fraction of its mass every second in the form of this invisible stream. It bathes the Earth, which is protected from most of it by its own magnetic field, and it flows past every planet and every moon and every object in the solar system, and it keeps going. Past Neptune, past the scattered disk objects at the solar system's outer edge, past everything with a name, and then, eventually, it loses. The space between stars is not a perfect vacuum. It has its own material, the interstellar medium, a thin soup of gas and charged particles that fills the galaxy and has its own pressure, its own wind, the accumulated exhalations of every star in the Milky Way. The sun's wind pushes outward. The interstellar medium pushes back. Somewhere between the sun and the nearest stars, the two pressures reach equilibrium, and the solar wind finally slows to a stop. The boundary of that equilibrium is called the heliopause. Everything inside it, every planet, every moon, every spacecraft still within its reach, exists inside a bubble the sun has inflated with its own breath. The Earth, the Moon, the asteroid belt, all of Jupiter's storms, Saturn's rings, the distant ice worlds beyond Neptune, all of it, every piece of the solar system we have ever visited or observed directly, sits inside a single structure that the sun maintains by simply existing and burning. That bubble extends roughly 120 times the distance from the Earth to the sun, which is to say, roughly 11 billion miles in the direction the Voyagers were traveling. 11 billion miles of solar influence, of the sun's wind filling the space around it, before the interstellar medium pushes back hard enough to say, "Here and no further." The heliosphere is not a perfect sphere. The sun moves through the galaxy, and as it moves, the pressure on the leading side is greater than on the trailing side, so the bubble is compressed in the direction we are heading, and stretched into a long tail behind us, the way a comet's tail always points away from the sun. We live inside a comet, essentially, a vast, slow magnetic comet, with the sun as its nucleus and the planets as its inner structure, moving through the galaxy at roughly 50,000 miles per hour, carrying everything inside it along on the journey. The Voyager spacecraft, by the time they were crossing the planetary system's edge, were still inside this bubble, still the suns, still within the reach of the same magnetic field that deflects the worst of the galaxy's radiation, still riding in the same medium that has surrounded the Earth for its entire history. The boundary was ahead, not close on any human scale, but definable, real, measurable, and the instruments on both spacecraft were already beginning to detect the first signs of it. The solar wind was changing, not because the sun was dying, not because of anything catastrophic, simply because, at this distance, the wind that had left the sun's surface at 1,000,000 miles per hour had been traveling for so long, through so much space, that it was spreading thin, losing coherence, beginning to feel the resistance of what lay beyond. The edge was announcing itself the way edges do, not with a wall, but with a gradual strangeness in the numbers, a change in the texture of the data, something in the instrument's output that made the scientists sit forward in their chairs and look a little more carefully. The first hint came in the form of a disagreement. In the summer of 2003, instruments aboard Voyager 1 began returning data that some members of the science team believed showed the spacecraft had crossed the termination shock, the boundary where the solar wind abruptly slows. The charged particle counts were behaving strangely. The numbers pointed, to some interpretations, toward a spacecraft that had already crossed. Stamatios Krimigis, the principal investigator on Voyager's low-energy charged particle instrument, and Ed Stone, the mission's project scientist since 1972, pored over the data with their teams. The magnetic field measurements did not agree with the charged particle interpretation. The spacecraft had not crossed. Not yet. Science does this, argues with itself in the data, in the gap between what one instrument says and what another says, in the space between what the theory predicted and what the numbers are actually showing. The arguments are not failures. They are the mechanism. When two instruments on the same spacecraft disagree about where the spacecraft is, the disagreement is itself information about the boundary's nature. The confirmed crossing came in December of 2004, when Voyager 1 was roughly 94 times farther from the Sun than the Earth is. The solar wind, which had been traveling at hundreds of thousands of miles per hour for the entire journey, hit the termination shock and abruptly slowed. Not gradually, not over millions of miles. Abruptly, the way a river slows when it spreads into a wide, shallow delta. The same water, the same material, but suddenly compressed and thickened and moving at a fraction of its previous speed. The temperature in the slowed wind jumped dramatically. The particles that had been streaming in cold, ordered lines became a churned, heated mass, piling up behind the shock the way water piles up behind a stone, pressing forward but having nowhere clean to go. This region, between the termination shock and the heliopause beyond it, is called the heliosheath, and it is not smooth. It is turbulent, foamy, confused, a place where the sun's spent breath mingles with the first pressure from the interstellar medium, without either side yet winning. Voyager 2 crossed its own termination shock in August of 2007, at 84 astronomical units from the Sun, 10 astronomical units closer than Voyager 1's crossing. The difference matters. 10 astronomical units is roughly 900 million miles. The two spacecraft were in different parts of the sky relative to the Sun, one heading generally northward out of the ecliptic plane, and one moving more southward. The fact that they crossed at different distances told the heliophysics community something they had modeled but not yet confirmed. The heliosphere is not a sphere. It is pressed inward on one side by the pressure of the interstellar medium and stretched on the other, shaped by the sun's motion through the galaxy. The bubble has a geometry, and the Voyagers had now measured 2 points on its inner wall. The heliosheath both spacecraft found was stranger than expected. The models had predicted a reasonably well-behaved transition zone. What the instruments found was a region full of stagnant pockets, reversals in particle flow, magnetic field directions that changed unexpectedly. The sun's wind, in its final miles before the true edge, was not going quietly. It was turning back on itself in places, piling up, confused and pressured by the resistance it had been building toward for 120 astronomical units. And still, the spacecraft moved through it, taking measurements, sending data home on signals that now took more than 13 hours to arrive at Earth, reading the interior of a structure that had never been measured from inside before. Ahead of both of them, still years away at their pace, was the last boundary, the heliopause, the true edge of the sun's domain, the place where the solar wind stopped entirely, not slowed but stopped, and the interstellar medium began. Beyond that, something no instrument had measured from the inside of a solar system, the actual dark between the stars. Somewhere between the stars, a world drifts without a sun, no orbit, no destination, no warmth from above, only the faint light of the galaxy itself, spread thin and cold across a surface of ancient ice. The stars here are the same stars visible from Earth, only brighter, unfiltered by any atmosphere, sharp and still in a sky that has never known clouds. The ice underfoot is smooth, where the cold has had billions of years to settle it, cracked in long, shallow lines, where something deeper shifted once, and then was still. Nothing moves. Nothing has moved here in longer than memory can reach. The galaxy turns slowly overhead, its center a soft smear of pale light low on the horizon, its arms spreading upward and across, patient and enormous, and the world beneath it drifts on in silence, going nowhere in particular, belonging to no one, carrying its cold through the dark the way all lost things carry themselves, steadily, without complaint, unchanged. There is a date that gets cited, and a caveat that usually gets left out, and both of them matter. On August the 25th, 2012, Voyager 1 crossed the heliopause. By the measure of the plasma environment surrounding it, the density and temperature and magnetic behavior of the particles the spacecraft was moving through, it was no longer inside the sun's bubble. The solar wind had stopped. The interstellar medium had begun. A thing built by human hands, assembled in a California laboratory in the 1970s, was moving through the space between the stars. The word interstellar gets used carefully by the scientists who work on this mission, because honesty about what it means matters more than the size of the headline. Voyager 1 is in interstellar space in the plasma sense. It has crossed the heliopause and is now bathed in the medium that fills the galaxy between its stars. But it remains, in the gravitational sense, very much a part of the sun's family. The sun's gravity extends far beyond the heliopause, beyond the scattered disk where the last icy bodies orbit. There's a vast spherical shell of cometary material called the Oort cloud, and the outer edge of that cloud sits perhaps 100,000 times farther from the sun than the Earth does. Voyager 1 will not reach the Oort cloud for roughly 300 years. It will not pass through it for 30,000 years. It will not be truly beyond the sun's gravitational reach for a timescale that makes human history look like an afternoon. So interstellar, yes, in one real and meaningful sense. Free of the sun, not yet, and not for a very long time. The crossing itself was not witnessed in real time. That is not how spacecraft science works at this distance. The data arrived continuously, the instruments recording whatever the environment was doing, but the interpretation of what that data meant, whether the heliopause had been crossed, and when exactly, required months of analysis and one crucial piece of evidence that came not from the crossing itself, but from an event that had happened at the sun more than a year earlier. In March of 2012, a large eruption on the sun had sent a wave of energy outward through the solar system. By the time that wave finally reached Voyager 1, in the spring of 2013, it had been traveling for more than a year. When it arrived, it set the plasma around the spacecraft vibrating at a measurable frequency. Ed Stone and the science team, working through the data, recognized what that frequency meant. It described the density of the surrounding plasma, and that density was roughly 40 times higher than anything measured inside the heliosphere. They were not inside anymore. Working backward through the records, the team identified the moment the plasma environment had permanently changed. August the 25th, 2012. On that day, Voyager 1 was roughly 121 times the Earth-Sun distance from the Sun. A signal sent from the spacecraft on that day, traveling at the speed of light, took more than 17 hours to arrive at Earth. The sun's light itself, traveling the same route in reverse, would take more than 17 hours to reach the spacecraft from the moment it left the sun's surface. The spacecraft was so far away that it had fallen outside the sphere where daylight, even at the speed of light, arrives promptly. Voyager 2 crossed its own heliopause in November of 2018 at a slightly shorter distance on the other side of the heliosphere. Its crossing confirmed what the models had suggested. The boundary varies with direction, shaped by the sun's motion through the galaxy and by the pressure of the interstellar medium, which is not uniform in all directions. 2 data points on the outer wall of the heliosphere, each one representing the end of something and the beginning of something else. What lay around both spacecraft now was not empty. The interstellar medium has its own particle population, its own magnetic field, one running in a different direction than the heliospheric field, its own slow currents and pressures. It is thin, far thinner than anything we could create as a vacuum in a laboratory on Earth, but it is there, and it makes a sound of a kind that the instruments could hear, and still they moved outward the way they always had. Don Gurnett had been listening to space since before most people thought there was anything to hear. He joined the Voyager project at the University of Iowa in the early 1970s as principal investigator on the Plasma Wave Science Instrument, a device designed to detect oscillations in the electrically charged medium through which the spacecraft would be traveling. Not sound in the way we normally use the word, because there is no air in space to carry pressure waves, but plasma, a gas of free electrons and ions, can oscillate in ways that are mathematically equivalent to sound waves, and an instrument sensitive to fluctuating electric fields can detect those oscillations record their frequencies, and if you choose to translate them into something human, ears can process, play them back as tones. Gurnet had spent decades translating the radio emissions of Jupiter, the whistling magnetic fields of Saturn, the strange crackling of the heliosheath, into something a human being could hear. Every major boundary the Voyagers crossed, his instrument had something to say about it. When Voyager 1 finally entered interstellar space in August of 2012, it was Gurnet's team that delivered the confirmation. The density measurement, the frequency shift, the 40-fold thickening of the plasma outside the heliopause, the numbers that let them work back to an exact date. But the finding that stayed with him, the one he described in interviews as the most unexpected, came years later. A graduate student named Stella Koch-Acker was working through years of accumulated Voyager 1 data at Cornell University, looking for plasma wave signals in the records from the period after the heliopause crossing. She was searching for the discrete events, the short bursts of oscillation driven by solar eruptions that had been the primary way of measuring the interstellar plasma density. What she found in between those events and underneath them, and running steadily through all of them, was something nobody had specifically gone looking for. A hum. Not intermittent, not triggered by anything from the sun. A continuous low-level oscillation in the plasma of interstellar space. The medium itself, vibrating gently at roughly 3 kilohertz, persistent and quiet, and apparently constant. The interstellar medium was not waiting silently between events. It had its own voice, faint and steady, the background tone of the space between the stars. Acker and Gurnet and their team published the finding in Nature Astronomy in 2021. 3 kilohertz sits near the upper end of the range a human voice can produce. When the oscillations are translated into audio, the frequency converted into a pressure wave that speakers can reproduce. The result is a thin rising tone, almost ghostly, not quite like anything else. Not music, not static. Something between those. It is the sound of emptiness that is not quite empty. Gurnet died in August of 2022 at the age of 83, 50 years after he had first attached his instruments to a spacecraft aimed at the outer solar system. He spent those 50 years listening, and in the last years of his career, a graduate student working through his data found that there had been something to hear the entire time, that the dark between the stars was not silent, but was, in its own way, always talking, at a frequency too faint and too continuous to notice until someone sat down and looked carefully at the ordinary moments between the obvious events. That is a pattern in this whole story. The obvious events are not always where the meaning lives. Morabito was not looking for a volcano. The pale blue dot was not a science priority. The hum of interstellar space was not what anyone sent Voyager to find. The mission kept producing its most resonant discoveries in the margins, in navigation images, in the data between the data, in what a graduate student noticed while looking for something else entirely. By 2021, Voyager 1 was more than 14 billion miles from the Sun. Its signal, arriving at Earth after roughly 19 hours of travel at the speed of light, still carried Gurnet's instruments' data in it, still recording the gentle oscillation of the medium around it, still translating the texture of interstellar space into numbers that a receiver in the California desert could hear. still talking, still being listened to. But the spacecraft's voice was getting harder to maintain. The power source that keeps both spacecraft alive is a kind of slow fire. 3 radioisotope thermoelectric generators, each one using the natural decay of plutonium-238, convert the heat of that decay into electricity. There's no combustion, no moving parts, no fuel tank to run dry in the traditional sense. The plutonium simply decays, steadily and reliably, releasing heat, which becomes current, which powers the instruments and the transmitter and the computers aboard. The process began the moment the generators were assembled, and it has not stopped, but it has slowed. Plutonium-238 has a half-life of 87.5 years, meaning the power output drops by a predictable amount every year, roughly 4 watts annually, which sounds like almost nothing until you understand that both spacecraft are now running on approximately 40 watts of power. 40 watts. Less than a common incandescent light bulb from the household of the people who built them. That is what is keeping contact alive across more than 22 billion miles of space. As the power has dropped over the decades, instruments have been turned off one by one. Not as failures, as decisions. The teams at JPL sit down, weigh which systems are still returning useful science, and which can be sacrificed to keep the essential ones running a little longer, and they send a command. The command travels for nearly a full day before it arrives. The instrument goes quiet. The remaining power is redistributed. The spacecraft keeps going. By 2023, Voyager 1 had been operating for 46 years when something went wrong with one of its flight data system computers. The spacecraft began sending back data that was garbled, not corrupted in transit, not a problem with the antenna, but scrambled at the source. One section of memory on a chip inside the computer had failed. The project manager at JPL, Suzanne Dodd, and her team faced a problem with no easy precedent. The code running on Voyager's computers was written in the 1970s, in programming languages some of the current engineers had never used professionally. The original documentation existed, but the people who wrote the code were mostly retired or gone. The chip could not be replaced. No human hand would ever touch that spacecraft again. Every command sent to investigate the problem took almost 23 hours to arrive, and every response took almost 23 hours to return, a round trip of nearly 2 full days at the speed of light for a single exchange. The team worked through it over months. They identified the damaged section of memory and found a way to reroute the affected code around it, splitting the software across other available memory locations, like water, finding a path around a stone. In April of 2024, Voyager 1 began returning clean, usable data again. A spacecraft 46 years old and more than 15 billion miles away, repaired with a workaround that took months to design and communicate, by engineers, some of whom were not yet born when the spacecraft launched. That is the texture of what it means to maintain contact at this distance. Not dramatic, not cinematic, just patient, careful, extremely slow motion problem solving conducted across a gap of space so large that every conversation requires a day and a half. The gap is only growing. Every second, Voyager 1 moves roughly 10 miles further away. Voyager 2 moves roughly 9 miles. By the time you finish listening tonight, both spacecraft will be measurably further from the sun than they were when we started. not by much on any map you could draw. But the numbers keep moving, and they only move in one direction. There will come a point, probably within this decade, possibly later, when the power will no longer be sufficient to operate any scientific instrument or to heat the electronics enough to keep them from failing in the cold of deep space. The transmitter will go quiet, not because the spacecraft broke, not because anything went wrong, because the fire that has been burning since 1977 will have dimmed past the point where it can carry a voice across 20-something billion miles of nothing. When that happens, both spacecraft will still be going. The plutonium will still be decaying. The golden records will still be sealed. The instruments will still be pointing, more or less, in the directions they were last aimed. Everything will continue, in silence, in the dark, at roughly 35,000 miles per hour, in two directions, forever. Here is what all of it points toward, if you step back far enough to see it at once. 2 spacecraft, built in 4 years on a budget that would not fund a single modern mission, designed to last perhaps 5 years in space and return data from Jupiter and Saturn before going quiet. That was the plan. That was the ambition. And those machines have now been running for nearly half a century, sending data from beyond the edge of the sun's domain, still being heard, still talking, repaired from the ground across gaps that light itself takes a full day to cross, kept alive by engineers working in programming languages the world has largely moved on from, monitored through antennas pointed at a part of the sky where nothing visible lives. The discoveries were not, mostly, the ones anyone planned. The volcanoes on Io were an accident of navigation. The ocean under Europa's ice was an inference from fracture patterns. The hum of the interstellar medium was found in the margins between the events everyone was actually looking for. The pale blue dot was a photograph the scientists who built the cameras argued against taking. The greatest gifts this mission gave us arrived sideways, through the instruments pointed at something else, noticed by someone who was looking for something different and found something better. That is not a story about luck. It is a story about what happens when you keep showing up long enough. And the silence coming, the gradual dimming of the transmitters, the instruments going dark one by one, the eventual end of contact. That was never a failure written into the future. It was in the design from the beginning. The plutonium was always going to cool. The power was always going to fade. The spacecraft were always going to outlive their ability to speak. What was never in the design, what nobody wrote into any specification, was that the speaking would last this long. Consider what it means that they will keep going. Not for years, not for centuries, though they will cross those too. Both spacecraft will drift through interstellar space for billions of years, long after every language spoken on Earth tonight has changed beyond recognition, long after the civilization that built them has transformed into something unrecognizable or ended entirely, long after the sun has expanded and brightened and eventually swallowed the inner planets in its old age. The Voyagers will still be going. The golden records will still be sealed. The plutonium will have long since cooled to nothing. The transmitters dead, the computers dark, but the physical objects, the aluminum frames, the gold-plated copper disc, the instruments pointing at nothing in particular, will still be moving outward at roughly 35,000 miles per hour. through the dark between the stars. In roughly 40,000 years, Voyager 1 will pass within 1.5 light years of a faint star in the constellation we call Camelopardalis. It will not stop. It will not be pulled in. It will simply pass at enormous distance and continue. In 300,000 years or so, Voyager 2 will come within a few light years of Sirius, the brightest star in our night sky. It too will continue. There is no destination. There was never a destination. The grand tour ended at Neptune. Everything since has been passage, the longest, slowest, most patient passage any human-made object has ever undertaken, and it will not end in any time frame that has a name we use. The golden record, if it survives 1 billion years, and the engineers who designed it believed it would, will have outlasted the surface of the planet it came from. Earth's surface, geologically active and eventually subjected to a brightening sun, will not remain the Earth we know for anything like 1 billion years. The record will be out there in the dark, carrying Anne Druyan's brainwaves and the sound of a Javanese gamelan and the brainwave of a woman thinking about love long after the world that made those things is unrecognizable. These are the longest lasting artifacts our species has ever produced, not by a small margin, and still they moved outward, the way they always had. Above the plane of the galaxy, the view is different. The spiral arms spread below, vast and faintly luminous, turning so slowly that no human life is long enough to notice the motion. The stars here are older, not the young, bright blue giants of the disk, but ancient suns, dim and patient, gathered in loose, spherical clusters that orbit the galaxy's center in long, slow paths that take hundreds of millions of years to complete. These clusters are called globular clusters, and there are hundreds of them, and each one holds hundreds of thousands of stars in a space barely larger than a few hundred light years across. A soft, dense glow against the dark, visible from anywhere in the galaxy, ancient as the galaxy itself. From here, the Milky Way is a horizon, a flat, faintly glowing structure below and around, its center a soft orange warmth, its arms curving outward and away into a darkness that has no edges. There's almost no sound here, because there's almost no medium to carry one. Only the faint hum of plasma, thinner than any vacuum manufactured on Earth, drifting between the stars in slow, invisible currents. The light from the nearest globular cluster takes thousands of years to arrive. By the time it reaches you, the cluster has moved slightly in its orbit, and the stars within it have moved slightly in theirs. And everything is in the same place it always seems to be from a distance, which is to say still and ancient and unhurried. A clock that has been running since before the sun was born, measuring time in units too long for the word to hold. Something small drifts through this. Two somethings, very far apart now, moving in different directions, neither one aimed at anything, both of them carrying the same faint residue of warmth from a star they left behind decades ago. They are not large enough to see from here. They are not large enough to matter by any measure the galaxy uses. But they are here, in the halo, in the old light, in the slow turning dark, and they keep going. The title of tonight carries a weight that it does not need to carry. Lost contact. As if the spacecraft wandered and we could not find them. As if something went wrong, something failed, a signal dropped and a connection severed. But that is not what is happening, and it is not what will happen when the transmitters finally go quiet. The word lost belongs to things that disappeared when we were not looking. These two did not disappear. We watched them go. We tracked every mile. We sent commands across 20-something billion miles of space and waited 2 days for the answer, and the answer came back. And we sent another, and we will keep doing that until the power runs out and the voice goes still. And when it does, when the last signal arrives, and the antennas in California and the Atacama and outside Canberra fall quiet, and there is nothing more to hear, the spacecraft will still be going, still carrying the record, still moving outward at 35,000 miles per hour through the dark between the stars, in the same direction they have always been going, without hesitation, without needing to be told. You cannot lose something that never stopped. Everything they showed us is still true. The volcano on Io is still erupting right now as you listen to this in the dark. The ocean under Europa's ice is still there, still sealed, still waiting. The great dark spot on Neptune has come and gone, and the planet's winds are still the fastest in the solar system. The pale blue dot is still what it always was. 1 pixel in a sunbeam, everything. The hum of interstellar space is still sounding at 3 kilohertz, and no one needs Voyager to keep listening for it anymore, because now we know it's there. The knowledge does not fade with the signal. They were never going to come home. They were always going to go further than we could follow. We knew that in 1977, and we sent them anyway, because some things are worth building even when you know you cannot keep them. That is the most human thing in this whole story. Not the engineering, not the science, the decision to build something, send it out, watch it go, and say, "Good, go. We are glad you are going. Rest now. The spacecraft are still moving. The record is still sealed. The dark between the stars is humming, faintly, at a frequency just above what any voice can reach. And somewhere out there, in 2 directions, 2 small machines are carrying everything we thought to put on them. And they are fine, and they are going, and they will be going long after the last person who ever heard this has found their sleep. Good night.